Hey there, awesome physics students. Let's talk about conservation of momentum. Probably one of the most fundamental and important ideas in all of physics, and I'm not overstating that. Well, let's start talking about money. If I have $5 and I give my friend $5, then I now have $5 less than I did before. And we do this all the time, and we understand that underlying all of this, there's a conservation of money law at the local level. Of course, I realize that money does not work like this at large scales on economies and countries with the central banking system and all that. But on the small level, if your friend suddenly appears with $5 and it seemed to come from nowhere, you would be very suspicious of that, because you know that in order for them to have $5 more than they had before, someone else must have given them that $5. It has to have come from somewhere else. Momentum is just like that, and that is the basic idea of the conservation of momentum law. If something gets momentum, if it gains momentum in a particular direction, that momentum had to come from somewhere, from some other object. Some other object now has momentum in the other direction. Okay, let's start with Newton's law and our understanding of momentum as the rate of change of the force as the rate of change of the momentum. Now, if the external force on a system of objects, and I'll say a little bit about the system in just a second, if the net force on that is 0, well, you can see from this equation here that this means that the change in momentum is going to be 0. And if there's no change in momentum, that means that the momentum vector, the total momentum vector, must be constant. Now, what do I mean by a system? Well, the idea here is that you have some system of objects that you define, and those objects are exerting forces on each other, and they are exchanging momentum as they exert those forces. And if you take those forces and you consider them the momentum change they are creating, that those forces will always be equal and opposite, and the momentum exchanged will always be equal and opposite. And if you add those momentum transfers up, you'll get 0. Now, this is kind of abstract and hard to get your head around. So let's think about a particular example. Imagine you're standing on ice, you're goofing off with your friend, and you put a force on your friend, or you push on each other. So you push on your friend and your friend pushes back on you. Because of the third law, these two things have to be equal and opposite. Now, if I just focus the system, if I say, okay, how am I going to define my system? Let's define my system as just being me. Then in that case, clearly I feel a net force in this case, and I'm going to experience a change in momentum because of that net force. Well, that's not very useful to understand this conservation law, because we want there to be no net force. What you need to do in that case is change your system, change the way you define your system. You need to include both the object and the agent that causes all of those the other force, in your system. And so now if you expand your system to include all of the things that are exerting forces on each other, now we can write out the initial momentum is going to be 0, because we're both standing there to begin with. And then the final momentum at the end, after we push on each other, is going to be my momentum, which points this way, and then my friend's momentum, which is going to point that way. And remember, these are vectors, so direction matters. So I have to add these two like vectors. And when I add these two like vectors, they're going to add to 0, and I'm going to have the same constant momentum that I had in the first place. In this particular example, the constant is 0. It's not always 0. This helps us understand forces as a different kind of thing. Instead of thinking as forces as, okay, you push me, and then for some mysterious reason I push you back with an equal and opposite force, now we can understand forces as actually exchanges of momentum. And knowing that you cannot give momentum without it coming from somewhere, it must have come from the agent of that force.